You ready?
Yeah.
Okay. Woo! Excellent. Again, I'm Matthew, and I'm actually legitimately thrilled to be here in Vancouver. It's been several years. Love this city. I'm looking forward to hanging out tomorrow and eating ramen and just enjoying what Vancouver has to offer. And just a little about me and like this weird thing, the C# artisan, like what's that about? Right? So sometimes people ask the question, computer programming, is it an art or a science? Right? And my answer is like neither. At least for me, it's a craft. Now I know there are legitimate computer scientists out there researching, inventing, right? Pushing the boundaries of quantum computing and AI and crazy giant graph databases. And I have some of these people who are friends, and I try to get them drunk before we talk because they're too smart. So yes, there is computer science. And then I think most of us have experienced there's an artistic, aesthetic side to it. Good code looks nice, reads nice. It's aesthetically pleasing. But day in and day out, I am paid to build stuff that works. Right? It's artisanal. So I view myself as like a kind of a high-tech bricklayer. Right? I'm an artisan. And I like to teach and educate, and my kind of angle is helping those of us who are doing this work just get better at the craft of it, right? A lot of people can cobble together some code, but to be good, you have to kind of go to the next level and learn some stuff. So I view myself no different than you, right? I've learned a few things, I've been doing it a little bit, and I like to share some of the insights I've had. So that's a little about me and what motivates me and why I'm here. So if a few of you walk away from this going, huh, cool, or oh, I can use that, fantastic. Other markers of success, if you want to connect on LinkedIn, you can take a photo of this, right? Love to connect with people, that's cool. I do have this YouTube channel, C# Artisan. There's a lot of videos there. If you think I'm funny, go ahead. It would be awesome. I would love it if you would all subscribe to the channel and watch some of the videos and do all those viral, likey, things.
Like and subscribe.
Exactly. Exactly. So, but that just helps me kind of do this, right? I'm not getting rich. I'm not monetizing it. It's just about having fun and educating and building some community. So, thank you all for coming out. So, async await. So, how many of you have actually written an async await function? Right? Yes. Right? This is just bread and butter. It's really hard to write C# without using these two words. So I want to admit that I had done a lot of it, and one day I was kind of poking around, and I kind of had the sneaking suspicion that I actually didn't understand what the heck was going on. And I kind of ran into this wall and had a sort of a WTF moment, an epiphany, had to kind of dig through it and learn some things. And so today, I want to just take you through that. I'm going to take you through my little journey of kind of understanding this. A lot of these code talks are about like, hey, here's this new platform framework technology widget. I'm going to teach you how to do it. That's not today. Right? This is a little more theory, a little more abstract and brainy. There's not a ton of code in these slides. So hopefully it's a nice change from some other things. All right, so to kick things off, we're going to see if I know how to use PowerPoint.
And for next.
Yeah. So just a couple of acknowledgments. First, I really want to thank my Uncle Mel. I have no idea where I'd be in this world today without Uncle Mel. Thank you, dude. You mean the world to me. I want to thank, that was a joke.
We're trying to figure out what.
So if the question is he kidding? The answer is probably yes.
There was a resemblance.
Thank you.
I could see
the good side of the family.
I could see the resemblance.
I want to thank my employer, CG Infinity. It's a consulting firm out of Plano, and they're just super supportive of these activities. They're very encouraging. It's a great place to work, and it's a very enlightened corporate culture. I've really enjoyed it. So thank you, CG Infinity. And of course, thank you, Nedhat, and all of you for coming on out. Thank you for having this .NET user group for showing up. Not you. This is the picture that is on your meetup. So that's your logo.
It's quite handsome.
All right, so async await is a form of parallel programming. And so when we think of parallel programming, to me, it all boils down to I would like my code to do more than one thing at a time. Okay? That's it, right? I'd like to do more than one thing at a time. And there are a lot of kind of paradigms and vocabulary that people use to talk about this sort of thing. Parallel programming, concurrent programming, multi-threading, asynchronous programming. They're all different. They have different emphasis, but what they have in common is this idea that my code is going to do more than one thing at a time. It's not just going to go through. So asynchronous programming, that flavor, oh, here we go, yeah. Got my slides backwards. So it's about doing more than one thing at a time. So async code, that kind of flavor of doing this, it really focuses on allowing your program to kind of stay busy or responsive while you're waiting on a longer process to complete, right? You've made a REST API call. You've done something. You're not quite sure when it's going to come back. And you don't want to just sit there frozen. You want to be able to kind of, whatever it is, keep the UI painting or service other requests, like let your code keep being responsive while this long-running thing is going. So that's the theory of async, asynchronous programming. But let's bring it down to reality. Okay, let's talk about a real-world problem that illustrates this. So anybody been to Japan? Yep. So you maybe recognize this, right? This is the kiosk in all these restaurants in Japan. Japan is a very interesting culture. It's very Japanese. It is Japanese. It's very cash-oriented, right? Everybody carries cash. And if you want to eat dinner, you go into a cafe, you pop some money into one of these things, and you push a button, and it prints a little ticket. And then, after you do that, what ends up happening is some people in the kitchen start cooking your dinner, and they call out your number, ring a bell, and you present your ticket, and you go get your dinner. So it's really awesome. I love, how different it is from what we're used to here. But let's just say, for hypotheticals, that you were thirsty as well as hungry. So you're like, I would like a drink to go with my dinner. So in Japan, the way you're going to go get your drink is at one of the 10 billion vending machines that line the streets. Like they have more vending machines than cars, I think. It's crazy. So you're like, all right, I'm going to go down and for 1 coin, 100 yen, I can get happiness. And you're going to put in the coin and get your drink. So you've got these two things, dinner and a drink. So if we were to do, this is a tech talk, so don't worry. So if you were to do a UML sequence diagram of this, and if you were to do it as a synchronous set of instructions, it would look like this. Okay, my get dinner function starts, and I'm going to execute this thing called order food, right? And that runs and it finishes. Thank you. And then I'm going to execute this other function called get drink, and then it finishes, and then I sit down and I enjoy myself. So that's the synchronous implementation of dinner in Kyoto. The async version, at least in my mind, looks something like this, where I put my money in the machine, and I press it, and then I get to leave the store and walk down the street and go get my drink and come back and then wait a little bit, and then my food's ready. And so they're overlapped. Right? Two things are happening at the same time. Now, do you order your drink first, or do you order, I don't care, right? It doesn't matter. We've kicked them both off, and once they are both done, I get to sit down and enjoy. So there's two UML sequence diagrams modeling a synchronous or an asynchronous implementation of dinner in Kyoto. So now, let's write it in C#. All right, so I'm going to go nice and slow through this. Right? So I've got an HTTP client, whatever. It's in implementation detail. Let's say it's been configured and it's ready to go. So I have this top task, async or function, async task, get dinner in Kyoto. And it awaits order dinner, and it awaits order drink, and then I get to enjoy my dinner and my drink. So here's the implementation of my order dinner function, which is async. It returns a task, a generic task of type dinner. And in this case, I've implemented it as some REST API call to the restaurantkiosk.com server out there on the internet. And I've got a couple of query parameters, item 29, option is rice. And right, so here's the async, right? I await that. And then when that finishes, I check to see if I actually got what I wanted. And then I deserialize it, you know, the body of the HTML into JSON, and I have dinner. Everybody following so far? We went really fast from like food to code there. And then the order drink is the same, right? It's a different server, thedrinkmachine.com, but it's basically the same thing. And then enjoy, you know, yum. Okay, so this code, which UML sequence diagram does this code implement? First one or the second one?
First one, right?
Who thinks first? Okay. Who thinks second? Who is just happy to be here and is hungry now because I've been talking about food?
You're going to wait on the first.
Yeah,
and then
exactly.
You're going to wait on
Okay, exactly. So the thing is, when you call await, the code pauses there. I didn't say blocks, right? I'm being careful with my language, but the reality is this line, await order drink, doesn't happen until this line completes. So this C# implementation is the first one. So when I bumped into this, I went, wait, what? Like, what the heck? Why are we even doing this? Like, what's the point? Like, I want this other thing that really, I was just like, almost to the point of like, I'm going to stop writing async code because it's dumb. I don't know what it does, and I don't get it. So that's the epiphany, or the question. We're going to go through the answer now. What it actually does turn out to do something very important. It has a reason. And we're going to go through that. And we are also going to look at how you would get those to be overlapped. There's some simple C# code that lets you implement the overlapped version. So we'll do that too. But there's the question. I posed the question. So now, right before we move into the answer, I did order the chicken pork combo. And you know, people think of Japanese food, you think of ramen and izakaya and tempura and all this, you know, sushi, of course. But actually, regular, that's all there. You can get all that. But regular Chinese people, when they get off work, often go to a cafe and get something like this. Cheaper, filling, hot, fast, yummy, good Japanese food. Okay, so what does async await actually do? And the answer is, it is all about the thread pool. When you start a C# app running, you are allocated a pool of threads, thread pool threads. The relationship between them and operating system threads is interesting and technical. I'm not even a super expert in that, so it doesn't matter. You're given these threads, and every time you create and run a task in C#, it gets assigned to a thread pool thread. So the real thread pool that you get with your app has thousands of threads. I don't remember the number, 68,000 or something. But let's imagine, for the sake of the discussion, that we have this sad little thread pool, which has exactly 3 threads. I didn't want to draw 68,000 boxes. So we have 3 threads. And there you've got an app. And this is your thread pool. And your app responds to requests that come in. And a request comes in, and you need to service the request. So our first request, why is my slide out of order? Dang it. All right, we're missing a slide? Maybe? Anyway, there was supposed to be a slide that showed just the first one. You're going to have to imagine here. When that first request comes in, and it starts running, it gets assigned, say, T1 out of the thread pool. Now, in your processing of the request, you've got a bunch of steps, right? Step 1, 2, 3, 4, 5. And it just so happens that step 3 is kind of slow. It's like maybe a call out to some unreliable web service, right? Another microservice or a web service API, something you need to access. So T1 starts, and it gets there, and it's just kind of busy waiting. And then a second request comes in, and a third request comes in. And so now all of our threads out of the thread pool are allocated. So they're all busy. They're not doing much, because they're kind of just sitting there waiting. And then a fourth request comes in. So this is called thread starvation. Right? You're out of threads. Sorry, you just have to wait. So basically, request 4, out of luck, until these other ones complete and threads become available. So thread contention, which is just like fighting for available threads, and thread starvation, like where you're completely out. This is the problem that async await actually solves. This is what it does.
Would you say there's a pool of 68,000?
Something that's a very large number. It's a surprising, your thread, the initial thread pool that C# gives you, it's configurable, but it's surprisingly big. Okay, and if you do some tracing on your thread pool and you just do a simple console app and a few things, you're like, oh my gosh, why have I got 14 threads going? There's a lot that the framework kind of does. Yes, sir?
Yeah, they're virtual threads, actually, because at the end it has to go either to GPU or CPU, right?
Yeah,
Depends
so
pretty much on the machine.
right. So you're asking the question of how does C# map, and also there are not just thread pool threads, there are dedicated threads you can create. There are 2 completely separate flavors of C# threads. I have about a 10 video series on YouTube channel on threading, on threads and multi-threads. You can go check it out. But what you're asking about is like, what's the relationship and the mapping between an operating system thread and kind of a virtual C# thread? And I'm going to dodge that question because I don't feel confident of giving a really solid answer. But you're right, it will ultimately be limited. Right? Now, so much of the code that we run these days is in the cloud. And the actual hardware is such a weird abstraction. Right? There's a blade and a Docker container and a Kubernetes and an Azure function. So it's a good question. And so I think you're right. Just to call them virtual threads, I think is a good way to think of it. Okay, so we're going to rewind that story about the slide I didn't show you about the very first request that comes in. Right? So when we implement this as async await. So this request 1 is now async request 1, and we have an awaiter here. Here's what happens. When the code gets to the await, it creates this thing called a continuation. So there's your vocab word for the day. That's your new concept, if you haven't heard of it. So a continuation is a kind of bookmark, hence my little icon, right? Basically, it says, okay, this call stack, this line of execution, it got to this point and it can't progress. So we're going to bookmark it there. We're going to let the thread go back to the pool, and we're going to listen for a magic signal that tells us we need a thread back because we're ready to move to step 4. Y'all follow that? Right? The continuation, basically, its purpose is to say, here's where you're going to continue when whatever that is that you're waiting on is done, with a drink, when you get back from getting your drink. And it allows the thread to go back. So you can see then what the effect of this is. It doesn't take a ton of imagination, which is that when request 4 comes in, you now have any number of threads available. Even though these guys all have continuations, they're all awaiting, plenty of threads available to service that new one. That's what async await does. That is the problem it solves. Okay. So just to complete this story, now let's say that request 1 has finished. We got our information back from our REST API call or whatever, and we heard that magic signal. We are going to talk about that, right? Being vague on purpose. And it's like, cool, give me a thread. And then you get another thread out, and it gets to keep going. One thing I did in the diagram, which is intentional, you notice that the thread that it resumed on is different than the thread. It started on T1, and it resumed on T3. This is extremely common. And if you do thread tracing with your async await code, you will see there is no rhyme or reason for which threads you get. And as an aside, if you've ever been tempted by things like thread static, the thread static attribute, it does not, it really, things go very badly for you if you port that code to async await, because there isn't this affinity, right? There's no kind of coupling between a line of execution or a process, and a virtual thread, right? As you await, every time you await, when it comes up for error and starts running again, you're going to get a different thread. So there's ways around that. There's a video on that. I have thoughts and opinions, but that's not what today's talk is about. So that kind of completes the story of what happens. In summary, async await really isn't designed. It doesn't allow code sort of inside your function to do multiple things at once, like I thought. I thought that was the point. What it actually does is it frees up thread pool threads so your application overall can do multiple things at once. It makes your overall app more responsive. And where this really comes into play is like in ASP.NET Web Services, where you don't know how many requests are coming in. Could be 100, could be 1,000, could be 10,000, right? And you don't necessarily know what kind of hardware you're backed by, and so your app needs to do this. And I were theorizing, where did this come from? Why did Microsoft introduce this? And I have a totally unproven conjecture that it was the ASP.NET team that actually pushed for this, because they needed people to write code in a way that didn't just throttle their framework by sitting on every available thread, which is easy to do. So no proof at all for that. Okay, so yes.
Quick question.
Yeah.
Let's just, if you go back to your code sample, for example, right?
Yeah.
And you made your two methods not asynchronous, it won't run any faster overall on a single request, right?
Your function itself. Yeah, so if you blocked, if you said await.
No, you just didn't even have await or async, you just had them both.
Well, you can't, because it was we're going to come to that too, because it's an HTTP client.get async. There is no synchronous HTTP client.get. There isn't a synchronous.
I think, is there no non-asynchronous get?
But let's just say that you did .get await or .get result, that you made it, you forced it to be synchronous, which you can do, which we'll talk about. That's right. Your code within that function, I don't think would be
any faster
affected in any way.
But would it solve the problem, or are you saying that the async solves the problem of instead, like you get 1,000 simultaneous requests to the same method, and you would get thread starvation at that point? You would not get thread starvation?
Not even the same method. Your app overall, right? A request comes in, and there's this cascade of function calls, some of which have to call out and are async, and some of which aren't. But that you can overload the thread pool, right? By having everything kind of sitting there synchronously waiting for these long calls. That's right.
Can I share one opinion, just?
Yeah.
Just opinion. So, if I consider low-level programming, it would make your code faster if you launch a thread pool and that function is dividable into the small chunk. Then the thread pool, I guess, behind the scene, can divide the one function into several different threads, and then it does it faster when it returns. So, when thread pool launches, it depends on the task. Some tasks are not. For example, if you calculate pi is definitely is chunkable. So you can launch 15 threads and divide the task into 15 threads.
This is the perfect
segue. If you say hello world, it's not chunkable, so technically you get one.
Tell me your name.
Pardon
me?
Yeah.
This is the perfect segue. You've made a few propositions and asked a few questions, which we are absolutely now going to talk about. Because the next section is implications.
Sorry to be so.
No. It's great. No, it's perfect. Because I'm sure look, if you're having these thoughts and questions, other people are too, and I was as well. So I didn't mean to cut you off, but I wanted to say, yeah, this is exactly where we're going.
I don't.
Yeah, you need to address the blocking factor.
And you're so good thought. So okay, so that was like my confusion and my discovery of like what this is at, why it exists, and what it's doing. But let's unpack it a little. So implications and some analysis. And the first thing, just to get out of the way, is what I promised you, which is, let's say you really wanted to overlap order drink and order dinner. Okay. So the way you do that is in some variation that looks kind of like this. First, you create your dinner task. So when I create what I call order dinner, that starts running. Okay, I get a task back immediately, a task object, but I don't get the result. I don't get my dinner back. Right? I get the task. And then I call order drink. So now they've both launched, right? I've done execute async on both of them, and they're out there running. And then I use this static method of the task object. I say await task.whenAll, and I pass it an array of tasks. So if you want to run tasks in parallel inside your function, you have to make a list or an array of all the tasks that you're kicking off, and then wait for now, you could also do when any, right? If you want to start running when one of them finishes. There's some variations, but in most cases, probably what people want is when all. So this now actually is the implementation of your overlapped functions. Okay, so this is simple code. There's a few different, you'll see in examples and things, a few different like syntactic variations, but it basically boils down to initiate all the tasks that you want to run, package them in a list, and then wait on them. That's simple. The next thing is something, so the caption is turtles all the way down, which is this metaphor for like infinite regress. And this is something that maybe you have experienced. I'll take a poll in a second. So let's say we have this lovely non-async program where my main calls function 1 calls function 2 calls function 3. And it's beautiful. And then one day, we need to change the implementation of function 3. All of a sudden, function 3 needs to do something async, like HTTP client get async. Now, we got a problem, right? Because you can't call the async method inside the synchronous function. Compiler won't let you. So, you're like, I can solve that. I'll just turn it into static async task function 3, which shifts the problem up to function 2, which now won't compile because you see the problem, right? So now it's turtles all the way down. So you're like, oh, you know, I get paid by the line. We can fix this. And so your code ends up, you're like, okay, well, I make this one static async task. And so the only purpose of that is so I can call function 3. And then the only purpose, right? And then I kind of get back to main. And it's like, what do I do here? What do I do about my main? We'll solve it. But so who has had this thing where you've got a nice program, you introduce one async thing, and then it's like this fractal thing. Like all of a sudden you have to, like your whole program becomes async, weirdly. Has anyone, you're nodding, but people, yeah. So this is, I call this the turtles all the way down problem. So the reality is there is always a synchronous, asynchronous boundary. Right? Your program and its relationship to the operating system is not async. Windows, Linux, they don't understand C# async continuation JAWS. Right? So there is always, you're always crossing that boundary. The question is just how you do it, where you do it. And so the simple way, let's just take this specific example with the main, where I could say, here's my non-asynchronous static void main, entry point to my program. And I say function 1 dot get awaiter dot get result. This calls an async function from a synchronous context. There's other ways you can do it. You'll see examples of like create a task and get the result. I did some kind of reading and thinking, and I can't say I 100% understand why, but this is the recommended approach that I believe. So if one of you discovers that it's no longer the recommended approach, this is supposedly less likely to have certain kinds of deadlocks that other techniques can have. So you can see, right, we're going from synchronous call context to asynchronous call context. And the cool thing is you can choose to do that wherever you want. You don't have to like have this infinite regress all the way back to the entry point of your program. I would say, kind of from an architectural standpoint, this is just like exception handling. You don't want like willy-nilly, like what throws and what catches, right? You have to make decisions up front. Like, this is the level of my code where I'm catching everything. Anything downstream of that can throw safely, right? And anything upstream of that can be assured that I'm going to catch. You have to make those choices. So same thing here. You've got a mix of async and synchronous code. Just think about like where are we crossing that async sync boundary. But that's the syntax we're doing.
I think you have to be careful with that when you're looking at anything that's like Razor or Blazor or any kind of UI-driven application, because it's going to go terribly for you.
Yeah. So UI is an interesting subset of async code where you want responsiveness. This is a fantastic point. So yes. So I know they're keeping me a little bit on my toes. It's fine. And again, I don't claim to be the expert on all things. No,
like in a console, it's totally legit.
Right. Or even in like okay. Let me keep on going. Let's not get too far. Now you may know. I think it was C#8 or so. They actually, maybe 9. They started allowing us to declare our main functions for a regular program as async. So you can do this, but what it's actually doing is the C# compiler is doing this behind the scenes, something like this, where the actual entry point to your program that Windows sees is this other bit of magic. So it's a little bit of your razzle-dazzle that C# does for you. Just so that you're aware, there is a transition between synchronous and async. And of course, you can, again, the most common thing is these ASP.NET apps where your controller methods can all be marked as async explicitly from the get-go. And then something in the framework is taking whatever the external TCP request is and marshalling it into your, injecting all of the middleware, and by the time your code starts running, a lot of stuff has already happened. Right? One of which is you've been given an async context. So that was my turtles all the way down kind of exposition. The next thing gets to exactly, I'm not going to remember his name. He's not paying attention. He's going to fail the course. He's teasing you. So we're getting to your point, which is what makes something awaitable in the first place. So to explain that, we have to talk about this concept of IO-bound versus CPU-bound work. And I now understand why this didn't work, is that it didn't save correctly, because I changed this slide too. So that's fine. So IO-bound work versus CPU-bound. Let's start over there. CPU-bound work is work that's limited basically by your CPU, your processing capacity. So the speed and number of cores that you have accessible to you, like math stuff is a really great example. One app I worked on, we were doing really huge median calculations on like arrays of 1 million. And the only way, there's no shortcut to a median. You have to sort the dang thing and find the middle. And if you add one number or change one number, you have to resort the thing and find the middle. We're also doing like nonlinear regression, right? These kind of big math calculations. So those are CPU bound. They have high CPU utilization, and you're right, the optimization is you focus on parallelizing these. And then there's this other class of work, which is IO-bound, where it's all port-based, right, or disk-based. Like I'm reading and writing from the disk, or I'm reading and writing from a port. They really don't use the CPU very much. And the optimization here is to use asynchronous programming. So async await is all about the IO-bound stuff. We will get to the CPU-bound stuff, but that's really the world that it exists for. And if you do a quick tour through some of the popular .NET namespaces, and you look for the async functions, like system.net.http, HTTP client has get async, patch async, both put, delete, send. Microsoft Data SQL client has a set of async ones for opening a connection async, execute reader async, execute non-query async, execute scalar, etc. Of course, your system I/O namespace, you've got all these file operations. You can read lines async, read bytes async, read and write async. the service bus, which is something I love. I'm a big service bus guy. I might get send message, and these I know for sure do not have non-synchronous implementations. There is no send message. There's only send message async. Send messages async, schedule message async, cancel scheduled message async, receive message async. All of those. There's some weird things. Windows storage, not as common, but there's some file IO class that does things. Named pipes, kind of old-fashioned. Some of us has done some named pipes programming, even like within system security cryptography. So what do all of these things have in common? They're all IO. In fact, they're almost all TCP. But it's all IO, disk, port, IO. So it's the world of IO-bound tasks where async await really shines. And so let's go back to this slide, which was supposed to be up earlier too. I guess I deleted the wrong one. So when the continuation gets set and the thread returns, remember I said we start listening for the magic signal that says, okay, you're allowed to continue. So what is that? That's kind of a mysterious thing. And so on Windows, it's an IO complete. There's this thing called IOCP, which is a Windows API. It's basically built into the operating system. It's a piece of Windows that says when you're going to do a port, like an IO request to this disk or this TCP port, I will give you back your physical thread, and I will subscribe you to this port, where you're going to get a message on this port that tells you it's done. So you go have fun, right? So this is actually supported at a very low-level operating system kind of thing. On Linux, it's a different function. Like the different operating systems implement this concept in different ways. So basically, all of those async functions that I showed you, under the hood, they're all doing some C# magic, which is some import of the Windows libraries, right? If you've ever done direct Windows programming in C#, you have to import the functions and use pinvoke and run all this stuff. So that's what's happening for you under the hood. So like not anything is awaitable. The things that are awaitable, they're extremely common. We use them all the time. These are the things that are awaitable, is these port, basically, operations. So that's the secret sauce that is possible.
Just to reiterate, you said in your earlier slide there, you said for IO bound threads or this one, yeah. So it's both of them, right?
This is all of those functions are here.
Yeah.
I have one slide on C. We will talk just briefly about that.
More about CPU right now.
But if that was the problem you were trying to solve, you would not have invented async await. You would use just tasks, which have been part of C# since version 3 or something.
Yeah.
You don't need the extra syntactic support that makes it easy, that async await gives you.
Right. Okay.
So IOCP, IO completion port, is the weird secret sauce that we're all getting for free. Okay, so what about CPU bound? Right. So here's a small example of CPU bound. I've got a little class called job info. So my job has an ID, and maybe this is totally fake, but I've got a decimal seed, an integer of the number of iterations you want me to do, and then the data I want you to operate on. Make it up, whatever that is. Bizarre hash algorithm, or so you're implementing your own cryptocurrency and you want a new hash algorithm. So that's a job info. And then I have this function called get work to do, which returns a list of those. Right? Could be a million of them, could be 2 of them. And so it makes this list, and then based on something, right, some input, it configures a whole bunch of those jobs to do. So far, so good? And then we have this async task to do a bunch of CPU bound work. So first, we, for each, this code is not quite right. Let's not basically for each job info in get work to do, in my list, could be 1 item, 0 items, 1,000,000 items, create a task by calling task.run. That's the key. For CPU-bound work, you have to call task.run. You can't just execute the task and wait. Right? That's important. So you call task.run, that gets your task going, and then I'm going to add, oh, this is my result list, right? So I add it there, and then I do await task.whenAll. So, right, this is how you would kind of parallelize. Now, what's cool about this, the reason this is so powerful is the task framework that's in C#, it can kind of figure out how many cores you have, and it does a really good job of scheduling and load balancing. So if I've got a 4-core laptop and I put 28 tasks in this list, it's not going to start all 28. Right? It'll probably start 6 or 8 of them. Right? It makes very, very good CPU utilization, and you can watch this. Because if you started all of them, they would all like fight, right? They would all compete for my 4 cores. Whereas when I do it this way, it's going to start them, and as they finish, it'll put the next one in, and as they finish, it puts the, right? It kind of meters them out. So it gives you free load balancing and really good CPU utilization. So you run this code on 10 different computers, it does the right thing. I mean, you could write all that yourself, but it's really cool. So that's the really nice way to do CPU. If you happen to be dealing with CPU-bound work, and it's less common maybe than it used to be, but it still comes up. There's an even cooler way to do this, which doesn't require any async or any awaiters at all. No, okay. You can use the parallel for construct, which is one of my favorite underutilized C# language features. So same thing, we build a list of work, and then when this is what's new here. It's do a bunch of CPU-bound work, and we say give me a list of jobs, and then parallel dot for each. Pass in the jobs and pass in a little lambda expression that is the function to do. Right? Do a job. And it does it. So what parallel.forEach does is for each item in your list, it creates a task. And it tells the task-based programming execution thing to run it. And the only difference between the other version and this version, besides this is only like 2 lines of code instead of 8, is that the thread, pool thread, of this one gets, it sticks, right? That doesn't return to the thread pool. Whereas in the other one, because I called it await, that one thread pool thread gets to go back. But if what you're doing is like serious number crunching, that may not be a problem. And of course, you could make this an awaitable thing. There's a way to do that as well. So that is really cool. If you've never used parallel for, and you have a chance to, it's a really great technique. And again, I've got a whole series of videos that kind of walk through this in a little bit of detail. All right, so yes, questions?
So for the previous slide, if you don't use the task.run on a CPU bound, it's not going to work?
Because you have to then, you can't, it's not an awaitable, right? The action, that's a great question. Let me point it out. So do a job is not async task in a job. Do a job is just crunch my number, right? Like this is, and maybe this is not even your function, right? Like when I did that nonlinear regression jobs, I didn't write that. I don't know the Leavenworth-Marquardt nonlinear regression algorithm. I bought some code from a guy in Russia. And it worked great. So you see what I'm saying? Like this is not an async function. This is a CPU-bound function, so it doesn't have to be marked as async. So this is the way you run synchronous code. We talked about calling async code from synchronous code. This is calling synchronous code kind of from async task.
So is what you're saying is imagine do a job took 5 seconds to run, right? traditionally, if you put a for loop into there, you had 10 job infos to run. That's going to take 50 seconds to complete.
If you did them one after another.
If you did them in a for each, it's just like, yeah, just do a job,
Oh,
do a job,
yeah.
do a job, do a job.
Right.
And your timer's at the bottom. It's going to take you 50 seconds to complete, right?
Exactly.
What you're saying is, doing it this way with the task.run, it would take 5 seconds.
If there were 4 of them and you had 4 cores,
Yeah. Based on the number of cores or the machine, right?
Más o
The
menos.
processing of the machine.
Más o menos, right? There's a little overhead, but
Yeah.
yeah, basically you're exactly right. If you would be able to parallelize them and do them all.
So is this
Exactly.
parallelization or
Yeah.
is this task.run?
Well,
Because
This-
it is different. It's slightly under the cover, isn't it?
this
I'm
is
not quizzing you, I'm asking you.
Yeah, no, I understand. The reason we want to use tasks here instead of is because you don't want to have to write your own code that checks how many cores you have and deter. So if you did it just with your own for loop,
So here's my, let me
And you do
refactor
the-
the question for a second.
Yeah.
Could you just write this exactly with parallel for each do job in the code that you have right there?
oh,
And it would be the
parallel
exact same
for-
thing?
It makes a task. That's right. Parallel for each makes tasks.
Yes. Okay, so
Parallel for each is shorthand for
for the loop.
for this. It just doesn't have this
For the
label.
wrapper.
Yeah, exactly. Parallel for each is built on top of the task, the TPM, the task-based programming model. Yeah, TPM. That was the. Thank you.
Kind of, after that, you get it in 5 seconds. I think it's gonna be 50 seconds for this test because if you put it like the timer in the do job for wait for 5 seconds, this is still wait for 5 seconds for each. So it's a for loop.
But
No, it'll finish in 5 seconds.
it'll put each one on a different
but the
core.
function is not the synchronous function.
It doesn't
Doesn't
matter.
matter. That's the point.
This is the
That
right.
is the point.
So you're going to go back and think about that because that is exactly the
I
point.
would
This
love
is
to try that. Actually.
This is CPU-bound work, which means the only limiting factor is how many cores you have and how fast they are.
So
And if you know that one of those do a jobs can run in 5 seconds on one core, and you have 4 cores, that means you can do 4 of them every 5 seconds, assuming there's nothing else slowing you down again. So if this list was seeded with 10 items, what the TPM would do is it would probably put 6 out to start with, and then 2 would finish and it'd chuck another 2 in, and then 2 would finish and it would chuck another 2 in, and then they would come out. The algorithm is sophisticated about how it does it. I don't know what it does, but what I observe empirically is it's load balancing and trying to optimize your CPU resources for this kind of work. Okay, great questions. You guys are awesome. Let's just wrap up. Let's just summarize. So async await doesn't do what I thought it did. Maybe, are you surprised too? If I surprised you, then it's success. And the rest of you don't know. So under the hood, it's using IOCP and continuations to free up thread pool threads when doing lots of IO bound work. That's its purpose and how it's done. This allows high performance app to service many clients, many requests. You can run your own little tasks in parallel using task.waitall, your own IO bound tasks using task.waitall. There is always a synchronous asynchronous boundary, whether you know it or not, and whether it's invisible or not. That happens. You do get to control it if you want to. And CPU-bound work can also be parallelized with or without an await. Right? The await is not really necessary. TPM is necessary. Well, is the right way to be advised. Okay. It's a lot, but that is that's the end of the slideshow.